Hello. This talk is about the first industrial application of e-test. The application involves the ultrasound inspection of fault glue joints of car parts in a human-robot collaborative setting at Audi Brussels. My name is Joris DeSchutter. Some of you may know me as a member of the robotics research team at KU Leuven and Flanders Make, but I'm also involved in a company named Flexible Robotic Solutions, or FRS. And in the talk of today, I will present work carried out by FRS in collaboration with Flanders Make and Audi Brussels. A bit more on these affiliations. The robotics research team is both a university lab at KU Leuven in the Department of Mechanical Engineering and a core lab of Flanders Make, the Flemish Strategic Research Center for the Manufacturing Industry, which operates in close collaboration with the Flemish industry. On the other hand, FRS is an SME based in Leuven, providing industrial solutions so that robots or cobots can work in a very flexible way in an environment which is less structured and predictable. Hence, they provide solutions focusing on sensor-based adaptive or reactive control, human-robot interaction, and fast and intuitive programming. You can find more information on these affiliations on these web links. I also would like to acknowledge the support of Project FinRob, a Flanders Make project, and I will explain the name FinRob later in this presentation. The outline of this talk is that first I will present the application, industrial application, then I will briefly explain the approach and the implementation. Of course, I cannot give a lot of detail. And then also summarize what is our view on the benefits of using a constraint-based robot programming approach for such application, to end with a conclusion and outlook. The application is about ultrasonic or ultrasound, or in short, US quality inspection of fault glue joints of car parts at Audi Brussels. The car parts are doors, trunks, or hoods, and these parts are manufactured by joining two plates or two sheets. The outer sheet is folded around the inner sheet, and some glue is placed in between. That's the blue substance here. And what we want to do is, in the application, is to inspect the presence of glue using an ultrasound sensor. This is the inspection direction. We can also inspect from this side, but in this application, we inspect it from this side in order to make sure that the joint is properly closed. Now, the segment, the joint to be inspected, you see it here, it seems quite smooth, but if we zoom in, for example, on this section, you see that it is quite deformed. It has local deformations with respect to the CAD drawing due to the manufacturing process. And in particular here, you see marks of spot welds, which deform locally the shape of the joint. So then the question arises, how is this inspection done manually today in the companies? Well, one approach is, of course, destructive inspection. Here you see an operator who opens the joint manually and then inspects the presence of the glue, that is the blue substance that you saw. Another way is indeed ultrasound inspection, but manual inspection. Here you see the operator pressing the ultrasonic sensor against the part. And sorry, but the video stops. I will try to. So here you can see the operator is pressing the sensor against the workpiece. So he's using his tactile feedback. At the same time, he's watching the screen to look at the ultrasound signal. And if there's a good reflection pattern, he knows he has a good acoustic coupling. And then he presses the button using his remote control and does the recording. So, starting from manual ultrasonic inspection, which was only done at discrete points 2-3 centimeters apart, the specifications for the automatic inspection were that we needed higher resolution, more points. So the idea was to have a continuous tracking of the fault glue joint. Also, of course, we want to automate the adjustment of the sensor to achieve good acoustic coupling by both tactile feedback and interpretation of the US signal. Also in this application, the sensor that the operator was using was just a single element sensor, was replaced by a phased array US sensor with 32 elements, but maybe that's a detail for the discussion and I will not comment more on that. But very important, the company required that all the 8 different parts of a car would be inspected on the same cell with no clamping of the parts. And also they preferred a cell with a human-robot collaborative scenario using the KUKA EVA robot. Clearly, these specs introduce some challenges. I already pointed at the local variations in shape of the joint with respect to the CAD model. But the fact that 8 parts are inspected on the same cell, just placed there without any clamping, introduces a lot of positioning uncertainty of the part in the Cobot cell. And on the other hand, the use of a KUKA robot introduces several issues. First of all, the KUKA EVA is much too small to inspect such large parts. There is an insufficient workspace or insufficient reach. And of course, working collaboratively with a human and a robot introduces safety issues and also human error. So we have to provide robustness with respect to human error. The approach followed by Everest was then to implement a continuous contour tracking based on force feedback while monitoring the ultrasound signal. And if this signaling, if there's good acoustic coupling, is dropping below a certain level, the robot stops and makes a discrete adjustment to find a proper orientation for the sensor. The insufficient reach of the KUKA was solved by adding a degree of freedom. You will see immediately that the KUKA is hanging from a rotating table. So there is a turntable that was introduced as an extra degree of freedom in the system. And the safety issues and robustness with respect to human error were solved by a lot of monitoring, safety checks, and safety procedures. Here is an overview of the Cobot cell. You recognize the robot EVA here. And it has, of course, a joint torque sensing, which is very appropriate to do human-robot interaction, but it's not accurate enough to do this fine contact force sensing to do proper contour following. So we added a force torque sensor here at the end effector. Here is the ultrasonic sensor. As I said, a phased array sensor with 32 elements. Here you see the turning table, but the center of the table is here. What are the tasks to be performed by the operator in this collaborative scenario? Well, first of all, the operator has to load a support piece on which the part to be inspected is mounted. Then he has to load the part to be inspected. He has to guide kinesthetically the end effector with the ultrasound sensor to the starting point of the first segment to be inspected. And he's also responsible for dispensing a couplant fluid. That's a fluid that has to enable good acoustic coupling. Afterwards, of course, the operator has to unload the part and unload the support piece. Clearly, in a robot version, we would automate more things, like item 3 and 4 could easily be automated in a robot version of the cell. Here you see the cell in operation. There is a longer video at the Everest website. Here we see the operator dispensing the coupling fluid. The part is already mounted on the support piece. Then the robot automatically moves towards the first segment to be inspected. Since there is a large positioning error of the part in the cell, the human guides the robot and brings the sensor to the first point to be inspected on the first segment. And then the robot continues automatically to do the inspection. It adjusts the orientation of the sensor and then follows until the acoustic coupling drops below a certain value, as I explained. Notice that the speed here in this video is multiplied by 8. So sometimes the robot stops, adjusts the sensor, and then at the sharp edges, the robot retracts, goes to a new position, makes again an approach, and continues inspection. You see in this segment, the robot needed not many, if any, stop to correct the acoustic coupling. Okay, some words about the implementation. As mentioned during the introduction, Everest embraced the use of constraint-based programming and the use of ATASL. So here you see that several components, ATASL components, were built for common tasks like Cartesian motion control or joint space motion control, but also for the particular application that you saw in the video, the contour tracking, with an approach component, a tracking component, and a retract component. That constitutes the lower level of the controller. And on top of that, you have the finite state machine implemented in RFSM, which governs the discrete event-based switching between the system states, so between the ATASL components and the behaviors, the corresponding behaviors. As mentioned, the ATASL components are developed in a constraint-based way, of course. They contain the task-related constraints, but in addition, we had to provide several other constraints that have to do with workspace and velocity and so on. For example, very important is collision avoidance. As you can see here in the setup, the robot or its end effector can collide with the turning table here, can collide with the part, can collide with the table, can collide with the bridge here. This is supporting the robot. So we had to provide collision avoidance constraints, also workspace limits. And very important are, of course, the velocity limits. They're very important in general, also for other applications, but in particular for cobots, because there are very strict specifications of maximum speeds for all parts of a robot arm in a human collaborative setting. So in fact, Everest went through this procedure to make this system suitable for human-robot collaboration. So went through a certification process to certify this 7+1, 8 degree of freedom system as a Cobot. Of course, we had to monitor all these constraints. So we built modules, monitor modules to monitor the constraints, but I didn't show them in the diagram. I want to mention two special features of the implementation. First of all, programming new parts becomes very easy because you can use the force-based contour tracking for learning the shape of new parts. So that's the idea of fast and intuitive robot programming. The robot is programming itself. And in fact, fast and intuitive robot programming was the name of the project, the Flanders Make project. Another important feature is that Everest made use of switching to the KUKA-IWA sunrise controller for several subtasks and making use of a module that is available in the sunrise controller. For example, the kinesthetic guiding of the end effector to the first point to be inspected is implemented not by an ETASL component, but by a sunrise module. In the next two slides, I would like to summarize our experience with the constraint-based approach for this industrial application. First of all, we experienced that specification of advanced tasks is quite convenient. And I'm not only talking about the reactive sensor-based tasks like the force-based contour following, but also about the addition of other constraints related to workspace or velocity limits and collision avoidance, which are very, very important in an application with a high degree of uncertainty. Also, we experienced that tuning the parameters in ETASL is quite intuitive. I would believe that Erwin explained that the tuning parameters have a physical meaning. There are two kinds of parameters, the feedback gains and the weights. The feedback gains are relatively easy to tune since their magnitude is limited by stability and joint limits in terms of velocity and acceleration. So if you tune them up, then you run into stability problems and joint limit problems. So they are quite easy to tune and choose a good value. The weights are also intuitive to tune. We know that only their relative magnitude matters, corresponding to the relative importance of the constraints. But like others, we experience that the overall system behavior becomes less predictable when many constraints are active simultaneously. Also, we experienced that the change of platform is very easy. We added, as I explained, turntable as an 8th degree of freedom to the KUKA-IWA robot, which is already 7 degrees of freedom. And this went very, very smoothly. It just boils down to changing the model, kinematic model of the robot, and the rest is, involves no change. Also, we can rely on a good resolution of the kinematic redundancy in ETASL. A final word is about the switching. So we know that the library of components of ETASL that is available is quite limited, but we can focus on the development of new tasks, new applications, and in combination with switching to the commercial robot controller for the solutions and components that are already available. As a conclusion, I would like to say a few words about the results and the impact of this project. Clearly, this application, this automated Cobot cell, relieves the operator from a tedious task. It delivers consistent high quality measurements, which are recorded automatically, which can be archived and which can be analyzed later on in detail. It deals with a lot of geometric uncertainty. As I said, the position of the workpieces is uncertain, and also the shape of the workpieces is uncertain. It's varying and deviates from the CAD model. And the cell performs much faster than manual inspection. As for the impact, this application has attracted wide interest within the Audi VW concern. And the feedback from people in the concern is the following. Thinking in terms of behaviors instead of set points, robot set points, is quite revolutionary in industry. So I strongly believe, together with them, that there is a future for constraint-based approaches in real industrial applications. A final word of acknowledgement then. Of course, we used the following libraries in the application: ROS, Oracos, ETASL, RFSM. You can find more information here. I acknowledged already the Flanders Make project FinRob, and then I would like to acknowledge the collaboration of colleagues at FRS, Audi Brussels, and the robotics team at Flanders Make. Thank you very much for your attention.